Hello, everyone. Welcome back to our fourth day in the seventh GTDA school at CIMAT, Stochastic Topology and Topological and Geometric Data Analysis. So we have the pleasure to present now Ngoc Tran. That is right now has two positions, if I'm understanding correctly. So one is assistant professor at UT Austin, but also a Bonn Research Fellow at the Hausdorff Center for Mathematics, correct? Great. Yep. Yeah, Tran, Ngoc is going to be giving us a mini course, so we're very happy to have you here. Yeah, thank you very much.
Great. Well, thank you for joining. Yeah, I'd like to really thank the organizers for inviting me. I'm very sad I could not come to Mexico, but I'm very grateful for this opportunity. Yeah, and I apologize for the emergency that made me sort of mess up the schedule a bit. Okay, good. Yeah, so my goal of this talk is really to have some fun and hopefully get a lot of people just interested and to think about questions in recursive random partitions and its connection to probability, geometry, and machine learning. Okay, so let's have a warm up. Let's think about random partitions. So a partition of n is a set of positive integers that sum to n. Okay, so here's for an example. I have 4, right? I can write 4 as several different ways, right? I can write 4 as 4 plus 0, or 3 plus 1, or 2 plus 2, or 1 plus 1 plus 2, or 1 plus 1 plus 1. Okay, and each of these way of writing 4 as different sums give me different partitions of the number 4, right, into parts, right? So for example, and these these parts are called components, and these are the sizes of my components. And this can be ordered. This can be listed out by a Young diagram. So here's an example, right? So the number of components is the height of so Young diagram look kind of like a Tetris block, right? The height of the block tells you how many components there are, and the width of each level tells you how many things there are in each component, right? So here, this diagram says I have a partition of 4, and I put it all in one bin, and so that bin has size 4. Okay. Here I have another partition of 4, right? I put it into 2 bins, one bin of size 3 and one bin of size 1. Okay. It's common in, so the convention of the Young diagram is that you put the bigger sizes first. So this is why the Tetris blocks looks like that. So here's a pictorial representation of the partition of 4 into 2, 2. Here's 2, 1, 1, and here's 1, 1, 1, 1. Okay, good. Okay, so generally for partition of n, from arbitrary integer n, there are finitely many such partitions, right? You can list them all out using Young diagrams. Now here's the first question for you. How do I construct a random partition of n? So yeah,
someone can just
someone can unmute or type in the chat.
Can I take the token?
Yeah, please do.
Let people also to dare to speak. I don't know. Let's say I take 1 to n purple, and I choose one with probability 1 over n, one of the numbers.
Sure. Right. Yeah, that's a great recipe, right? So I take list out all the integers. You choose one, and then.
And then you have this part is one of the partitions, and this is other. I guess this is only 2 bins. That's the only thing.
Yeah. Okay. So yeah. So now you break it up into 2 parts, right? Okay, that's great. And then how would you say create a random partition of n with more parts?
Without compromising to have a certain probability distribution, I will say take one of these and do the same.
Yeah, that's a great strategy, right? So let's just recurse this, right? So now I just, perhaps you just want to randomly flip a coin, right? And decide which one to break further. And let's say you break this one further into two parts, you draw the same screen, right? So I mean, right. So that's exactly it. So this is called a discrete stick breaking scheme, right? So you can imagine it's like breaking out chocolate for, participants in a conference, right? So you start with n chocolate pieces, right? Or you can imagine eating them too. So take n pieces. You break it at random, and so now there's the x1 many pieces here and n minus x1 many pieces there. Let's say you eat all of these, and now you have so many left for the next day. And then the next day you break one off at random as well, right? So now you have x2 and you have n minus x1 minus x2 is left, and you keep on doing it until you have just one piece left. You cannot break it anymore. And then you just eat that last piece and you're done, right? Or maybe the last time you didn't, when you drew your random number, it turned out that you just want to eat the whole piece on the last day. That's also fine, right? So after recursing this, right, you get a random partition n. It's written as x1 plus da 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 plus xk, where the number of component k is also random. Okay, right? So this is a way to construct a random partition with randomly many components. So let's think a bit about this scheme. Let's do some probability now. Let's think a little bit, for example, what can I say about expected value of the number of components when n is large? Okay, so so let's do the simple assumption. These are the ones that Erika suggested, right? So let's have x1 be uniformly distributed between 1 and n. Right? So I have 1, 2, 3, etc., all the way up to n, right? This is to take x1 uniformly distributed. Let's say this was x1, and now condition on x1, right? So I eat this piece. I now have n minus x1, and now x2, right, will be a discrete uniform from this interval, which has length n minus x1, right? So I can think of condition on x1, x2 will be discrete uniform on 1 up to n minus x1. And then condition on x1 plus x2, this is this part, x1 plus x2. Then x3 will be discrete uniform on 1 comma the length of the rest. So let Kn be the number of components. What would be your guess for expected value of Kn when n is large?
Someone because I'm gonna completely just say I don't know, but something sublinear for sure.
Sublinear, yeah, for sure. Yeah, that sounds right. So like
Let's say logarithm
is much less than a constant times n. Okay, I think I'd agree. Yeah, there was a comment, please.
log n.
Log n, yeah. How did you get log n?
I don't know. I just imagine like half this algorithm.
Yeah, that makes sense, right? So each day, roughly, because I'm uniform within 1 to n, so the expected value of x1 is like n over 2, right? And now if I believe that each day I eat half of the bars, right, then next day it sounds like expected. So expected value of x1 is n over 2 for sure. Expected value of x2 is, maybe a little bit complicated, but it probably sounds like n over 4, right? Because just intuitive idea is that first day I ate about half of the bar, and second day I ate about half of the remain, so that's n over 2, and so on, right? So then because this is like kind of geometric series, right? This I do a half, a quarter, an eighth, and so on. How many steps until I reached about n seems like it should be about log n. Right. Well, more precisely, log base 2 of n. Right. Okay. Great. So, yeah, I would say expected value of Kn is about log base 2 of n is a really excellent guess. Right. But let's think a bit about why we couldn't have pushed that argument all the way through, right? Why are we still a little bit unsure whether that's the right answer, right? What makes this problem difficult? Why is expected value of Kn, why does that seem difficult to compute?
Someone wants to guess? Like,
right, so let me give a hint. So suppose I were to do like some kind of slightly different construction, right? Let me do it, yeah, so let me do something like, let me take x1 to be uniform 1 up to n, and let me also take x2 to be uniform, 1 up to, n over 2, and then, x3 is uniform 1 up to, n over 4, and let's say, right? And let me, wow, okay, maybe this example doesn't quite, let me just, for fun now, say, okay, say I want to construct a random partition of not of a fixed integer n, but let me say I want to construct a random partition of some integer with 3 parts, okay? And here's my recipe, right? And my partition now is going to be x1, the integer now will be x1 plus x3, x1 plus x2 plus x3. And if I were to ask you, okay, under this construction, I get a fixed number of parts, but the integer that I'm partitioning is random. And if I were to ask, like, what's the expected value of n, right? And this would be that easy, right? This would be expected value of n is an expected value of the sum, right? So even if I were to make these guys not independent, it doesn't matter because expectation is linear, right? I could do all conditioning thing here I want, right? But I can still, as long as I know roughly what's the distribution, marginal distribution of each, I can still compute the expected value, right? In this particular example, it would be something like n over 2 plus n over 4 plus n over 8. Okay. There's some rounding integer here, but this is basically the right idea. So so generally expectations of a sum, even if I don't have independence, expectation of sum should be fairly easy, right? So why is it that expected value of Kn, why is that? Why does that seem kind of hard to compute?
so can I say something?
Yeah, please do.
I guess the point is that here actually we have random variables in the uniform 1 to, it's not really n, it's a random variable that depends on the previous one.
Yeah, exactly. The problem is this part, right? Is discrete uniform from 1 up to n minus x1. So there's this dependence, right? That makes it really hard, right? You can think about it another way, which is whatever thing I do at the end, I have random variable x1 up to xk, and I have the way that I constructed it, it has to satisfy this constraint that I'm partitioning the integer n. So I'm, my recipe, it gives me a random partition that, of a fixed integer. So it induces this condition, right? It induces this dependencies between x1 up to xk, right? So that makes it, that just makes it kind of difficult to work with, is exactly this this constraint, right? And this constraint comes up in the way that we constructed, which is x2 has to be a partition of the remaining guys. Okay, so yeah, so here's a intuition that we talked about before, right? On average, we eat half the bar each time. So, the guess sounds good. The question is this correct? Okay, so so this is where, we should go away from the discrete world and let's think about what happened when n is really large, right? The advantage of working with large n is I can work with, say, a continuous approximation, right? So here's a continuous approximation. This picture is called the stick breaking scheme. And it's a recipe for breaking the interval from 0 to 1 into into a random partition. You can go on forever. So theoretically, with this scheme, you can go on with infinitely many parts. Each part will have like a real size. So, but it's you're breaking it up into numbers that sum up to 1. Okay. Okay, and how does the stick breaking scheme work? Right. So it goes first. I draw a point, right, uniformly at random, continuously uniformly at random between 0 and 1. So this is uniform on 0, 1. And now, it's the same business. Like I throw away this piece and I look at the remaining piece. Remaining piece has size 1 minus V1. And now I draw an independent V2, which is uniform on 0, 1, right? And so what I'm keeping track here, V2 times 1 minus V1, that's the size of the next part that I'm throwing away, right? So, right, because V2 is so if I normalize this stick here, the remaining stick, which has size 1 minus V1, I'm drawing a point V2 uniformly between 0 and 1, right? And then I times it by the length of the remaining stick. That will give me the size of the next piece that I'm eating, the next piece of chocolate that I'm eating the next day, right? And so what's left now, right, is, well, what's left now should be, same business. So it should be 1 minus V2, right, times 1 minus V1 is the size of, the piece available to me for the third day. And then here I would draw again a V3 that's uniformly on 0, 1, right? And if I times that with V3, then I get the size of this piece, right, of the piece that I eat on day 3, right? And so on. So you can see the recursion. So basically the picture looks like this. I have VI, which is an infinite sequence of IID uniform. And let me just keep track of how much I have after day K, right? So after taking 1 bite of chocolate, I have 1 minus V1, things left. After 2 bites, then I have 1 minus V1 times 1 minus V2. So after K bites, then I just have, 1 minus V1 times 1 minus V2 times etc. times 1 minus VK, right? Is how many, is the size of the remaining piece by after day K. Okay. So this is a continuous approximation, right? The idea is that if n is really large, right, then running the discrete stick breaking process for really large n is, after I renormalize or divide everything by 1 over n, then it looks like I'm just stick breaking a stick of length 1, right? That was discretized at the level 1 over n. Okay. And now, so I ignore the fact that I must break in increments of 1 over n. I'm just doing a continuous approximation. Okay. So how do I know when I'm done, right? So theoretically, this could go on forever. And that's a very interesting process by itself. But for this purpose of approximation, right, I should stop when I have less than 1 over n left, right? Because, well, I mean, yeah, I hope that's, because in the original process, right, I have n pieces for large n. In the renormalization, I'm just dividing by 1 over n, dividing by n, right? So now I have, theoretically, each piece of chocolate is about, it should be of size 1 over n, right? So this is a very small Toblerone. Each piece is very, very small. And for the first few days, I just ignore this approximation. But once I get towards the end, then I know I should stop if, I should stop breaking after I hit a piece that's less than 1 over n. Okay, I can just say at the last day, if I have this much pieces left, I just eat it all. I'll stop breaking. Okay. Okay. So that's, I hope that's process is okay. Right. So now let Tn be the number of bytes taken. Okay. So I hope you're, I mean, this requires a proof, but it's not too difficult, right? So we can say for large n, right, then the number of pieces in my stick breaking component in the discrete case, it's approximately the number of bytes I need to take in the continuous version until the first time that I get a p smaller than 1 of n. Okay, so kn is approximately tn, right, as random variables, right, in the sense that for really large n, right, these two distributions, they're not too far apart. Okay. Okay, so the point of doing this is hopefully tn is easier to work with. So what's the expected value of tn? First of all, like, why does this continuous construction seem easier? Or maybe you don't think it's easy at all. I don't know. But there's something about this construction that's, you know, that's yeah, that's kind of, there's something about it that's a little bit easier to work with than the previous one.
So I guess each VI is independent from the.
That's right. Excellent. So these VIs are independent, right? So all of these guys are independent. Right? And so after k bytes, if you fix k, then you know quite a lot about, you know, the distribution of the size of the guy that remains, right? It's just a product of ID uniform, right? These 1 minus guys are just also uniform 0, 1. So this is really a product of k IID uniforms. Okay, cool. All right, so we need to know, so we're just multiplying a bunch of uniforms together, and we're asking, we'll stop when we're getting smaller and smaller. We'll stop the first time that we hit below 1 over n. Okay. Well, so what can we say about this thing, the distribution of the number of bytes taken until the first time that I go below 1 over n? You can throw out vague ideas too. It doesn't have to be like, you know, I really don't expect people to solve this. This is a very legit research problem that, you know, came out of, you know, research papers of famous people. So yeah, if you have like some thoughts, I'll be very interested in hearing.
Yeah, anyone can unmute themselves.
You can also type in the chat, like, so yeah, so if I'm multiplying a bunch of uniforms together, like what's a good way to deal with that? Can I visualize it somehow? Like, is there a better picture than just, you know, than this picture here, which is like, you know, keeping track of this piece? Like, is there a different way to see it? Maybe if I keep track of like how many bytes I've taken, right? Then it would look something like this, right? First day I had 1, and then next day I have this, and next day I have that, and so on. I mean, is this picture easy, or is there another picture that we can draw that's a little bit easier?
Yeah, hello.
Yes, please.
So is it like choosing a random point in a high dimensional cube?
Is it like choosing a random point in the high dimensional cube? Okay, yeah, so so you have the continuous cube, right? If you take k bytes, then you're saying, okay, let's say I take 2 bytes. Okay, so then I have a square. Okay. And what do you mean by choosing a random point in the high dimension cube? Are you keeping track of these 2 coordinates separately? So this is,
yeah.
I see, this is 1 minus v1. This is like 1 minus v2, and then you're keeping track of this point. Yeah, okay. I mean, that's one way to see it, but I think that's kind of really fine information, right? Because I mean, there are some, yeah, because I mean, technically, I don't really care about the sequence. I only care about the product of the sequence, right? So this information that you're keeping in the cube is really fine because it tells me like not just the sequence, but even like the entire like kind of order of, you know, how the order of all the bytes that I've taken, which is very fine. The other issue with this representation is that you kind of the dimension of your space increase as you take more bytes, right? So if I take 3 bytes, then I'm kind of, you know, in the 3 cube, and I take k bytes, and I'm in a much bigger cube. So I think that's kind of, and also it wasn't kind of maybe not so clear. How do I know when I'm stopped, right? Because even if I know, let's say this point here, I guess you could draw the region that corresponds to, you know, all the points below here means I have hit below 1/n, right? And then, but then as the dimension of the cube changes, then the region that correspond to the product being less than 1/n, that region region would change as well. So that's but I like this cube. I think it's a very fine way of keeping information. Maybe let's do something a little bit more rough. Let's keep less information. What's a good way to think about, say, products of IID? Move some stuff. Okay, let's clutter. Oops. I think we already had an answer like a couple of slides ago, right? When people were talking about take the first byte and first byte is about size of half, and then second byte is about the size of half, and so on and so forth. And then somehow we end up with log n, right?
Yes, just take log. So this
Take
product will
log.
convert into
Awesome.
sum.
Thank you. Take log, right? So now log pk is now a sum of IID, right? Sum I from 1 to k of something, of log of 1 minus vi. Right, so this object is actually really friendly, right? Because log of a uniform on 0, 1 is actually, well, it's negative, right? Because I can be at most 1, log of 1 is 0, right? So this is a negative number. This thing, it turns out, the distribution of this like is a negative exponential 1, right? So this log of pk, it just turned out it's just a sum of ii, or minus the sum of IID exponential. So that sounds really friendly, right? That's just a if I took, let's take the minus, so then I have a positive sum, right? So what it is that now I plot this random walk. This is a random walk with positive only increments, right? So I start at 0, and then I have something, and then I jump some more, and I jump some more, and so on. Each the size of this is exponential 1. This is another exponential 1. This is another exponential 1, and so on, right? So I have basically an increasing process, and I'm looking for the first time in which I'm crossing the line, right? I need log of pk is less than log of 1/n, which is minus log n. So I need minus log of pk is bigger than log n, right? So I'm looking for the first time that I cross this line log n over here, right? So in my picture here, right, the very first k that I cross the line log n will be 5, and that will be, in this case, in this realization, this will be the value of right. So the key is this log is a sum of IID. So Tn is just the number of renewals on this interval 0 to log n. So let me draw a picture of the renewal process, right? Generally, a renewal process is a sum of IIDs which are positive, right? And yeah, and here is kind of exactly our picture, right? And so, right, so I'm just looking for a random walk with ID increments, and I look for the first time in which it goes above some level log n, right? And there's lots of classic results like central limit theorem in renewal theory, and essentially it tells us everything we want to know about this hitting time Tn, right? So this hitting time has an expected value, has a variance, and it has a central limit theorem. So Tn minus its mean divided by square root of the variance, it converges to the standard normal. And here are the parameters that matter, right? Is Tn indeed will be of order log n, but the constant here, we get it explicit. The constant is just 1 over expected value of the constant is 1 over expected value of the size of the jump at each jump, right? So, sorry, in the previous picture, I had these jumps, right? And if I look at the average jump size, right, then that's, expected value of this epsilon I, this is my mu, right? Similarly, I can look at the variance of the average jump, that's my sigma squared. And those are the two things that govern the asymptotic behavior of Tn, right? So, so expected value Tn is 1 over mu times log n. So this, let's qualitatively check this makes sense. So if mu is large, then that means I take on average like a really big bite each time. Well, then I should take not so much time to reach log n, right? So that means if mu is large, then expected value of Tn should decrease, right? So this thing at least intuitively makes sense, right? The variance is much harder to check, but here you see there's some thing that involves the noise to signal ratio, right? So mu over sigma is the noise to signal ratio of the size of the average jump, right? So here you expect that the variance of Tn, how much Tn varies, it's determined by it's determined by the variance of the pieces, but also how that variance relates to the size of the typical jump. Okay, so that's kind of intuitively, we can at least mentally check that these formula kind of make sense. Okay, so now we're done, right? We just plug in a bunch of formulas for the classical renewal theory. So for us, we have a product of ID uniform. So log of that is an exponential 1, right? So in that case, the mean and the variance is just 1. So expected value of Tn is just log n, okay? And the variance of Tn is also log n, okay? So asymptotically, the number of days to eat that Toblerone is normally distributed, mean log n, variance log n, okay? This holds for large n. Okay. Now, yeah, any questions on this so far?
So I have a question here. One then could tweak the size of the bar in such a way that with the same process have an outcome, desired outcome on the days that it takes. So for example, if one take something like, okay, any polynomial on n size is gonna be the same outcome, right? But something.
Sorry, what do you mean by taking polynomial on n size?
So if the size is not n, but is something that
yeah. So if you're not n, but you could take some function of n.
Function
right?
of n.
Yes, then you can use the same process approximation, right? I'm just looking for the time in which I'm go below, right? This function of n divided, well, just like something like 1 over that. So let's see if I'm n, yeah. So you have to figure out 1 over fn, right? Is what you want, because this is the size of one of your byte is 1 over fn, right? Once you normalize to 0, 1, right? This size is now 1 over fn. Yeah, so totally. So you can look at this and then you can go, okay, I look at Tn, how many TFN basically, how many bytes does it take for me until to reach, so TFN is the first time in which my renewal process reach log of Fn, right? So, right, and then you can play the same game and you can get some answer here for sure, right? I think you just, in that case, you just, because the mean and the variance stays the same, so then you just get a result that said log of Fn here, and this thing is also log of Fn here.
Yeah, okay, thanks.
So it was like n squared, then this will be like 2 log, right? 2 times log n. Yeah, great. You can also play with the size of the way that the distribution you pick of the jumps, right? So instead of saying I don't want to pick uniform 0, 1, right? Let me pick something else. And this is what people do. They pick like a beta AB or something, right? You need some distribution that's supported between 0 and 1. So I pick some beta distribution that changes this part. So now I'm looking at minus log of some beta. It has some distribution, has some mean, some variance, which one could compute, and then it will show up here in these constants. So yeah, so if you take, if we fix n, you always end up with order log n, which makes sense, but the constant clearly changes. Okay, great. Okay, so let's, yeah, so since this is a summer school, I try to perhaps give some good habits on, on how, like, I think once we done with a problem, it tends to be we declare victory and we move on. But let's just quickly look back to see, what have we learned from solving this problem? Okay. Okay, so before we encountered this problem, we said, oh, what makes this hard was we have this constraint, right? This conditional that was kind of annoying to deal with. And now, but we also had good intuition, right? We said on average, we eat half the bar each time. So we should let log n, log base 2 of n to be precise. So we got the order right, but the constant we got wasn't right, right? The actual answer was log n. So the constant should have been 1 and not 1 over log base 2. Right? So let's think about, so then, our solution was we had a continuous distribution. So why was the difficulty lifted? And perhaps a more interesting question is, why did we get the constant wrong? We thought it should be, log base 2 of n. Why is it not log base 2 of n? It's actually a fairly tricky question, I should say. Yeah. So it's okay to just sprout some ideas. I think in math it's important to have sort of just lots of initial idea at the beginning. So yeah, any thoughts especially from students would be great.
My guess is that you're considering higher order terms.
Higher order, okay.
Like this B1, B2.
Yeah, so you're saying, oh, maybe like this is like the first order term, and then there maybe should have been like some minus something here and then plus something there. Yeah. Yeah, that's really fresh idea. Yeah, I've never thought about it that way. Yeah, it could be. Yeah, it could be. But where would this, like, what's the meaning of these? Like, what would be the meaning of the second order approximation? Right? So you're saying, okay, I'm doing a first order approximation here, right? I'm going, on average, I eat the, half a piece, and that's why I end up with log base 2. Maybe I should have been more fine, and they say, oh, maybe I'm eating half the piece, but then I should actually have some adjustment on, that half, right? There's an actual distribution around that half. Yeah, I like that. Yeah, that's very cool. Although, yeah, I think off the top of my head, I wouldn't know what would be a good second order approximation. Yeah, if you have an idea on that, that'd be great. I'd love to discuss after. yeah, so roughly this answer is saying, oh, we were kind of too crude. Yeah, okay. So let's, here's what I think. So why was the difficulty lifted? Was, well, the continuous approximation gave us independence, right? So previously we were working with x1 plus yada yada plus xk. They have to constrain to be n, right? Later on here, I'm working with a much friendlier process, which is for each fixed little k, I'm working with like a product of IIDs, right? VI bars. This is the IID uniform. Okay, so so instead of like getting fixated on this n, making sure that I'm partitioning n, I just relax that a little bit using, and just run this process without worrying about n. And then later on, I say, oh, what I'm checking for is that pk has to be less than 1 over n. Right. So this is the part that I turn my k back into a random variable. But what I gain is that the underlying process I'm working with is a product of IID. Okay. So why did we get the constant wrong? Well, okay, so what we're doing, right, is we were looking at, basically this a half came from looking at expected value of a single byte. Right? So after taking log, this is what we're looking at: expected value of log of u. Right? U is the size of the byte. Right? So after this log transform, log of u is like the size of a typical log byte, and this a half came from making reasonings about what's the size of a sort of typical log byte. Right? Yeah, but what actually happened was, yeah, well, right. Yeah, so what if you write down the two reasoning process side by side, then you find that this argument would have been correct if we actually had this equality that expected value of log u is equals to log expected value of u, right? Yeah, so I guess, sorry, I made a mistake. So this log of expected value of u is what gave us the a half, right? Because expected value is a half, and when I took log, then I get log of a half, right? But expected value of log of u, this is the typical byte. This is what ends up being that mu in the constant of the renewal process, right? So it turns out that all we're mistakening here is expected value just doesn't commute with logs. Okay, all right, so let's take a 1 minute break, and we'll come back, and I'd like you to, during the break, you can perhaps look at these pictures and think about, in what way are they similar, right? What's the theme? Of these 9 pictures. Okay. Yeah, 1 minute break. I'll be back in exactly 1 minute. Okay, welcome back. Okay, yeah, anybody could find like a unifying theme on these nice pictures here? Or maybe more than one theme? What's you know, what do you think is kind of common about these pictures?
So someone said in the chat, fractals.
Fractals, awesome. Right, in other words, they're self-similar. And they self-similar in a kind of deterministic way, right? So now we want to look at processes like, you know, random partitions of space that are self-similar in a stochastic way, in the sense that the distribution stays the same when you zoom in and out, but the actual picture you get is kind of it's not the same. So let's look at recursive random partitions, and this is basically random fractals. And let's think about the case of dimension 1. Okay. So ultimately, we do want to generalize this to higher dimensions. If you've been to Eliza talk, you definitely saw, I hope, a few pictures of what these look like in higher dimensions. But yeah, let's go to very basic and look at what happened in dimension 1. So the plan is just to do exactly as we did before with stick breaking. The only thing is I'm not going to throw any piece away. Okay. So previously I didn't get self-similarity because because there's a clear left and a right end, right? Where I go, oh, uniform 1, and I'm going to throw this piece away. I'm not breaking it up anymore. I'm only break this piece, right? And now uniform 2, uniform 3, and so on. Right? But what if I didn't do that? What if I keep breaking these pieces later on as well? There's nothing that stops me from running the same process on all the pieces that I have. Right? Then what I get would, intuitively be a process that looks like this, right? And I could, formalize it like this. I have an interval of length L. Let's say for my picture, L is equal 1. And I have an exponential clock of rate L. Okay. So higher rate means the clock rings more often. Okay. So the first time my exponential clock ring, I'm going to break the interval uniformly at random. Okay. Okay. So let's say at U1. Okay. And then now I have 2 intervals, which I will keep track of independently. Okay. Each interval I now attach a clock. Right. And the way that I defined it, so if this is an interval of length L1 and this is an interval of length L2, this clock over here will have rate L1, and this clock over here has rate L2. Okay, so the bigger the rate, the more often the clock rings. Okay, and so this bigger interval has a higher probability of being broken first, right? Because then the first time the clock rings, I would draw a point uniformly at random in here and break this guy into half. Okay, and then I repeat, and now I have 3 clocks, and then I repeat, right? So yeah, does that make sense? So let me quickly switch. I prepared a simulation, so let me quickly. A small video. Wait, is this the right video? Sorry, let me find it first. I'm pretty sure I have one, but perfect. This is the right video. Okay, just have to make sure it doesn't play. Okay. Oops. Okay. So I apologize if I try to put full screen and my screen somehow goes a little crazy. So let's do this. So this is at the first time, right? So this is my interval here from 0 to 1, and you have this interval from 0 to 1 here, this imaginary interval. I'm just plotting the y-axis as well, just for kind of clarity. And now let's run this process, right? So this is what this process actually looked like if you simulate it, right? So the exponential clocks are pretty fast. This is a real, exponentials of rate 1, and each of this interval between these blue points, they have an independent clock, and the first clock that rings, and you get a new blue point. Right? So if I do it again, right, and it sort of looks like this. Okay, so after a while, I get a bunch of points on 0, 1, and this partition my interval into a random fractal. Right? Because the excitement is to do this in higher dimensions, but I think the analysis is much easier in dimension 1. Okay. Great. Okay. This is called a Poissonian rain. It's a model that's quite old and studied for quite a while in stochastic geometry. And the idea is you may imagine these are like raindrops, right? So you keep track of a vertical axis, which you think of it as time, right? And on this piece, from time goes infinity, and you have the ground, which is 0, 1, right? Okay, and now you imagine, there's a bunch of raindrops here. So these raindrops they're random, right? Well, how do I simulate these raindrops? Well, I mean, this is each one of these points. I draw on the x-axis. I draw a point uniformly at random between 0 and 1, and on the vertical axis, I just draw a point. Is an exponential with rate. Let's say rate 1. Okay, so I simulate this point process on this strip, this infinite strip, and now I watch as time goes forward. I watch as the rain falls down, right? So when this rain point fall down, it gives me this partition, and then the next rain points fall down, and then the next one, the next one, the next one, and then so forth, right? And this construction turns out to be exactly the same as this construction. If you're looking at the ground, then it's exactly the same as if you're waiting for individually each piece, the probability that, say, if I'm at this time t, and if I run like a little time, if I look at the rain just from here onwards, because these points were generated independent and at random, I can compute, what's the probability that a particular interval here will have a raindrop on x, right? That probability should be proportional to its length, right? Because the way that we constructed these points, right? Being each one of these points is a point of, x comma y, where x in particular has the uniform 0, 1 distribution, okay? Yeah, so the next point, its coordinate will be uniformly on 0, 1. So the chance that it lands in any particular interval will just be proportional to the length of that interval, and that corresponds to our our exponential clocks, right? So it works out. Okay, so let's think about this rain picture. How is this? So I said that this is self-similar, like a random fractal. In what way is this self-similar? So in what way is this thing a random fractal? I set an interval of length 1, right? I broke it up, right? Now I have 2 intervals random length, L1, L2, and then I play the same game, right? I wait independently for each of these guys. I wait until a uniform on this thing comes up, and then I break it up into 2 pieces and so on and so forth, right? So in what way is this self-similar?
No, I have one question there.
Yes, please.
So, for example, here in if we look at L2,
Yep.
the uniform distribution is going to be of within that L2, right? So perhaps this could hint of.
Yeah, definitely. Yes, yes. So if you say, oh, clock rings at L2, well, you know, how do we break up L2? We are drawing a point uniformly at random within this interval, and then we break it up, right?
And all the clocks are independent.
All the
right?
clocks are independent, right? Yeah, so I agree. You're definitely getting, you know, hitting it on the head over there. But let me just make it like, you know, a little bit more precise. So I think a good way to think about it is, okay, you know, we started with this interval 0, 1. And then the moment we broke it up, we had some interval of some other length, right? But we didn't have to start with an interval of 0, 1. Maybe we could have started with interval of length 0, 100, right? And we do it the same. We could define it the same way. We say, okay, I have a Poisson rain on top of this, right? I'm waiting for rain on a bigger, you know, on a much longer interval. Now, the first time the clock of this big interval ring, I'm going to, you know, see a petition, and then, you know, so on and so forth, right? Maybe I get some piece in 0, 1, 2, and then I keep on petitioning. Right? So how does this Poisson rain on the smaller interval, how does it compare to the rain on the bigger interval? This Poisson rain on 0, 1, 0, 100. Are they the same process? Like, you know, they have the same distribution in some way, or?
So can I say
Yeah,
something
please.
science fictional? If we could speed time or slow time, perhaps it will look the same.
You could split time. How would you like to split time?
Speed or.
Oh, you can speed time. Exactly. That's it, right? You can speed time like 100 times fast or 100 times slower, I think, right? And the well, like, yeah, excellent. That's exactly it. So the two, yeah. So this is self-similar in the sense that there's a way to trade time for space. Okay, so let's. This again, this is self-similar because there's a way to trade time for space, right? How do I trade time for space? Well, one thing I could do is I could simply scale 0, 1 to 100, right? So I look at 1, 0, 1. I run the petition on 0, 1, but then I just times it by 100, and so there we go. I have a petition on, you know, 0, 1 times 100. I'm not changing time, I'm just changing space, right? I'm just multiplying by 100, right? But in doing so, then the way we defined it initially was I'm looking at, I'm attaching exponential clocks of rate 1 to this interval 0, 1, right? So if I'm simply scale space, then I'm running the same process. If I look at it in terms of time, I'm attaching an exponential clock of rate 1, but to an interval of length 100, right? So that's not quite the process that I have initially. I should have, you know, if I want it to be perfectly the same distribution, right? I need a rate of 100 to this longer process, right? And if I do so, if I scale space and time the right way, then, you know, the scaled process is exactly have the same distribution as if running the original process on just a bigger space. Right? So you can formalize this. I mean, the formal definition looks really dry, so I didn't write it down. But essentially, you can say, okay, if I didn't want to change my point of view, if I'm just looking at 0, 1, how do I create a partition that runs basically that looks like, a partition on 0 to 100? I simply make times 100 times faster, right? So if I scale times by 100 instead of going, exponential 1, I run at the rate of exponential 100, and later on for each interval here, I will run at the exponential of 100 times L, right? Then the process that I simulate would look exactly as if I were running, the original process, but on like a larger scale, right? Because I see points breaking up a lot faster. Right? All right, and so you can also think about it the way as I start with 0, 1, and now if I keep zooming in to one of these interval, then it looks like exactly the original process, right? It's just it's the same in distribution, right? Namely, if I zoom in, if I after the first stick break say, I look at my interval L1 here, and now I ignore, I now only look at the process from the view of L1, then it will look as if exactly the same as if I was starting at 0, 1, but I run a slightly slower process, right? Because I have to wait for slightly longer before my interval get broken. So that's the kind of fractal quality of this Poissonian range, right? I think the key part here is you can trade time for space, and this is incredibly useful in probability. Okay, all right. So we can, and the other thing that's very cool is now you don't have to restrict yourself to an interval 0, 1 at all. You could, you don't have to restrict yourself to a finite interval. You can do an infinite long interval, 0, infinity, right? How do we do this, right? And so here is where it helps to think about not about the first time that a raindrop appear, because that time is basically 0, right? But it helps just to think about how do I constructed this as a Poissonian range. Namely, I started with a Poisson point process in dimension 2, right? Previously, I had a strip, and I had a Poisson point process here of rate 1, right? And so I get some points, and then I'm kind of sitting from the ground looking up, and I'm seeing the points as they fall, right? So here I could do the same thing. I could look at a Poisson point process on, of rate 1 on the positive quadrant, right? And I can sit here and look at the first time that things fall, right? So if I look at that entire line, then for sure, already at time, basically just time, any epsilon time above 0, I already saw infinitely many points falling, right? But if I focus myself just on any particular small interval, then I get some positive time before the first raindrop falls. Right? Okay, so this is a very exciting process in that you can now have a random fractal on all of R. Right? So okay, all of positive real, and then of course you can also generalize this to all of R. So I just have a Poisson point process on the entire upper half plane, right? And then as these point drops fall, right, already at any time, at any epsilon time above 0, you start with a random fractal, random recursive partition of R, right? And you can run time forward, and you can get, you can see sort of it densifies. And if you now look into like a small windows, and you can zoom in and zoom out, you see the same thing in distribution. Okay. So yeah, all right. So the arrival times of the raindrops from a Poisson point process, and this is why it's called Poissonian range. Okay. Yeah, so just a quick reminder, if you've never heard of what's a Poisson point process, it's a collection of random points such that if you take any observation window W, then the number of points in this region is Poisson with rate lambda times the area of this window, of the volume of this window in higher dimensions. And the key point is that if you have disjoint regions, then the number of points in the region are independent. Okay. So earlier I said, let's run the Poisson point process on R2, right? On 0, 1 times the positive real. So this infinite strip, 0, 1 times positive real. Okay. And what I mean by that is I have a point process that satisfies these properties, right? Namely that if you fix any observation window here and here, say, then the number of points in here is, Poisson with rate lambda, which I took to be 1, times the area of this window here. Okay, so you get, in expectation, you get, finitely many points, and points in different regions are independent. And the concept of time is just, I'm just interpreting the y-axis as time, right? So that's, and then I think about it as raindrops as I fall. I think about the projection of these points onto the x-axis. Okay, all right, okay. Yeah, so you can, I think this is a great exercise. If you're interested in this, you can use this formal description to prove very rigorously how to define this random fractal on all of R and to prove that this process is self-similar. Okay. Yeah, so let me quickly mention some applications. Why random partitions? This is very important in non-parametric base, right? I think one of the main application is clustering. So this is the stick breaking process we saw before, right? Which is so what's the idea here? I need so I have a bunch of points and I need to cluster them, right? So they come with labels and I need to cluster them, or maybe they don't come with labels, but I need to say how do I do that, right? So generally the problem is just, you think about it as each of these points has some value z. In this picture is in R2, right? So you have point z1 up to zn in R2. And my goal is to learn a labeling function, right? So my goal is to learn a function f that goes from R2 to the set 1, 2, 3, 4. Okay, that it will say, okay, this point zi, you belong to cluster number 1. These points z blah, zj, you belong to cluster number 2, and so forth. Okay, and so you can think about this as sort of learning a these parts are called the decision boundary and such. And one way to do this is the way of doing it, sort of the Bayesian way, is to say, first, I believe that some P1 fraction of guys should be in cluster 1. Some P2 fractions of guys should be in cluster 2. Some P3 fractions be in cluster 3, and some P4 fractions should be in cluster 4. Right. So these are the prior probabilities of points in clusters. Right. So this is the prior probability of, if I pick a point at random from my distribution, what's the chance it falls into each one of these clusters, right? Okay, so I have some prior probability prior, and then I see the data, and then data, and now I use Bayes' theorem, I recompute, and now I have posterior, which is a new vector of probabilities, P1 prime, up to P4 prime. Okay, so now what's the connection with stick breaking? Well, if we think about this, these PIs, they are numbers. They are 4 numbers that sum to 1, right? They're P1 plus plus P4. They sum to 1, right? So they form a partition of 0, 1 into 4 parts, okay? And what we're doing when we're doing this posterior, prior and posterior update is we're simply moving around on this probability simplex, right? Which is this simplex. This is the delta 4 minus 1, which is delta 3. So I have the simplex in dimension 3. Each point in here, I think of it as a tuple P1, P3, right? If you think about it as a picture in R3, then I have a simplex here, P1 up to P3. A point in the interior of the simplex is a tuple P1, P2, P3, such that P1 plus P2, it's just that these guys are all non-negative, such that the sum is less than 1. And then, I just define P4 to be 1 minus the rest, right? 1 minus the sum. Okay, so each point of the simplex is exactly a tuple P1 up to P4 that's conditioned to sum to 1. Okay, so this process here, I'm going from one point in the simplex to another, and I'm just moving around in the simplex. Okay, so yeah, so with Bayesian statistics, first of all, how do you come up with these priors? And the key computational point of coming up with prior is it has to be so that it works well with update steps. So now you can easily compute the posterior, right? And one way to do that is to get a prior, which is a random partition drawn from the stick breaking distribution. Okay, so stick breaking the stick 0, 1 into 4 parts, right? The way that we defined it literally, which was, to take a point, let's say uniformly at random, and now that's my pi 1, and now break it into pi 2 and break it into pi 3, and now this resting is pi 4, right? So that random process give me a distribution over the simplex, right? And that's really convenient because now I can kind of pick out a random point from this, prior distribution, and then it just so happens that I can tweak. I can tweak the stick breaking process so that the update step works really well. Okay, so here instead of doing uniform, I can do slightly. So a uniform 1 is a beta 1, 1, and in general people do beta AB. So now you have what's called hyperparameters, which are A and B, right? So in running this clustering process, you initially say, I choose A and B, and that gives me a distribution of stick break, and I choose A and B, and now that gives me a distribution of over the simplex, right? That they give me a distribution of random sticks, which then gives me a distribution over the simplex, right? And then I run this process with this prior, and it just worked. The updates worked really well, right? Precisely because of this really nice formula on how this product, this independence is really important here. Yeah, so there's really some really good overviews on this on non-parametric Bayesian clustering. It has applications, I guess, in the early days in topics modeling, where you think of each document as a bag of words and you want to cluster documents into topics. It's still used nowadays. It's a very robust method for clustering in high dimensions. So if you're interested, here are some links. So there's a blog that I think explains it quite well. There's also Tamara's thesis, Clustering and Features from Combinatoric Stochastic Process, that basically go over a lot of what we did today, which is random stick breaking, and a large part of the thesis is devoted to applications in machine learning. Okay. Yeah, so if you're interested, there's classic texts in combinatorial stochastic processes that more on the math and combinatoric side. But Tran has a really excellent book on random fragmentations and applications to phylogenetics and coagulations and things like that. Okay, so let me just want to give a preview of next lecture, since I only have 2 lectures, and I think just no more hard math. Okay. Can people hear me okay? I hope my connection's not too bad. Okay, so yeah, y'all good? Okay, great. Right, so that was the stick breaking stuff, and now, right, and so now we want to run. I mean, definitely the Poissonian range is more advanced, right? This random fractal, and the promise of the random fractal is that you can generalize to higher dimensions, and then you can use this process directly to, say, cluster data in high dimensions. Okay, so this idea was taken up by Roy and Tay, 2014, and they came up with what's called the Mondrian process. So this is basically generalization of the Poissonian range in any dimension. Right? It's a stochastic process that produces a recursive partition of space with random axis aligned cuts. Right? So in one dimension, my cuts is just a point, so I get Poissonian range. But in higher dimensions, it looks like this. It goes, I start with a square, say this 0, 1 square. Okay, and again, I have an exponential clock. When the clock rings, I Well, when the clock rings, I'm going to make either a vertical cut or a horizontal cut. Okay. And how do I decide which cut with what probability? I just look at basically the marginal process, which is the one-dimensional process, which is the process on the x-axis and the process on the y-axis here. Right. So initially, it's like thinking I have two independent Poissonian rain, one on the x-axis and one on the y-axis. Right. Now, so I effectively flip a coin, whichever one goes first, then I will draw a line uniform between 0 and 1, right? And you know, that's that line is my vertical cut, right? And now I have two squares, right? Here's a vertical square and the remaining square, right? And now I play the same game again, right? Each one of them, I attach an exponential clock. I should tweak it so that, you know, it gives me the right self-similarity, right? Roughly like proportional to the area, so, proportional to, I think, the sum of the diameter, right? Sorry, to the sum of the edges. Okay, so now whichever clock rings first, say in this case this clock, right? Then now I have two processes here. One is on the horizontal bar and one is on the vertical bar, right? And I think of these as basically like two sticks, right? And so I go, okay, now I know one of you two must ring the clock, right? And so now I wait, I have an exponential with this rate on the longer piece, exponential with the, you know, smaller rate on the smaller piece, whichever one goes first, say in this case, this one, then I draw a point uniformly at random and then make a horizontal cut, right? Okay, and then the process recurs. Okay, yeah, there's a really nice video. So let's pause, maybe we can watch some videos. Let me find the video. Okay, so this is a picture of the Mondrian process. And this is what happened when you zoom into a corner, right? So this is, they've sort of nicely colored it in the theme of Mondrian the painter, right? As you can see, it's pretty interesting. It has this sort of, it has this random fractal quality that, you know, you kind of got lost in space and time, right? Okay. Okay, great. So that's a simulation of the Mondrian in dimension 2. Okay. And you can definitely play the same game for Mondrian in high dimensions. So dimension 3, you start with a cube, right? Now you have basically three Poissonian rain you need to keep track of, one on the x-axis, one on the y-axis, and one on the z-axis. And now you play the same game, right? You wait some time, whichever clock runs first, you take a chop, right? Say if it were to, you know, the first point you drew were on the x-axis, well, then you would just chop, you know, with the hyperplane that's orthogonal to the x-axis, right? Chop it in, you know, at that point, and now you have two rectangles you repeat. Okay, that's the Mondrian process. Okay, so you can formalize this, you know, in terms of, you can think of it as sort of like a Poissonian rain, not a point, but of lines. Right? Okay, so I'll skip on how to formalize this. We'll look at it in next lecture. But a result of that is that a result of the thinking about it as Poissonian rain is you don't have to is now you can do cuts that are not axis aligned. And so this brings us to stable iterated tessellations. And the latest research, I think that's very exciting, is to use these techniques in stochastic geometry, where people study stits to solve, you know, problems in machine learning that comes out from applying the Mondrian process. Okay, so yeah, so tomorrow I'll talk about random forest, kernel tricks, and density estimation. Yeah, good. Yeah, great. So I hope to see you tomorrow. Not tomorrow. Wednesday. I hope to see you on Wednesday. Yeah.
Wednesday. Yes. Thank you very much, Ngoc, for this first session. I don't know. I think we have
yeah. Sorry, I
sort
of lost track of time. Yeah. So if you have any questions, you can email me and such, or you can also ask me first thing on Wednesday lecture. Yeah.
Great. Just let's perhaps give one chance for one question, and then we give a short break before our next. So someone has a question? If not, I suggest.
Great. Thank you very much. Thank you very much. Yep. Okay. Cool. Yep. I'll see you. Bye.
Thanks. Bye. So yeah, I think we will resume in 8 minutes. Yeah.